It's my pleasure to introduce Adam Afandi, who used to be a grad student here when he was young and happy. And now that he's older and happy, he's a postdoc at Münster University. And he's going to talk to us about stationary descendants and discriminant modular form. The format will be, as usual, like a little trailer talk, and then people that want to escape are allowed to do so, and then the regular talk.
Okay, yeah. Well, thanks for inviting me to give this talk, Renzo, and it's great to be back. Okay, so I want to give this trailer talk. We can sort of advertise the talk, take a quick break, right? After the trailer talk, and then if some of the grad students say, I don't want to deal with this anymore. So, okay, great. So let's start with defining the discriminant modular form. So let's consider this formal power series, which I'll call delta, which is defined this way. And there'll be a formal power series in the indeterminate Q. Okay, and yeah, so if you expand out this power series in Q, you'll get some terms, but let me define the terms you get as tau of n. Okay, so if you do this, you'll get, let's see what are the first couple terms, you'll get Q minus 24, Q squared, the next one will be 252, and so on. Okay, so these numbers that show up in this expansion, this is classically called the Ramanujan tau function, and Ramanujan tau function, and it's an object that's been studied a lot in number theory because it has really amazing arithmetic properties. So for example, here are some. So this is stuff due to Mordell. And then when Deline solved Debye conjectures, he also applied these following properties. So, for example, one property about this Ramanujan tau function is that it's multiplicative. So if you plug in the product of two integers that are relatively prime to each other, it splits this way. I should say, as long as GCD of n is 1. Another property is that if you plug in, say, a power of a prime, let's assume r is 0, then yeah, there's a nice expression for this. It goes tau of p, that's r, minus p to the 11, tau of p to the minus 1. Okay. Great, and then finally, there's a conjecture that goes all the way back to Ramanujan, and this is actually what Deline proved. He showed that if p is prime, then the absolute value of tau of p is bounded above quadratically in p. Okay, good. And so, yeah, so this Ramanujan tau function is really interesting because it has these nice properties, but even more than that, there's a very basic open question about it, which is we don't know if it never vanishes. Okay, so this is a conjecture that goes back to Raimar back in 1947, so it's been around for a while. And so, does the Ramanujan tau function never vanish? So by the first property, it suffices to show that this is true for n prime p. Okay, and yeah, so this is for my trailer talk. I want to sort of motivate the talk by thinking about this conjecture. And yeah, so it's been quite a while now since this was conjectured. Not too much progress has been made about it. However, there's a really nice strategy you can try. A nice strategy is what you do is you try to reinterpret the Ramanujan tau function in terms of something else. Actually, maybe I'll describe it as find what tau of n is really computing. Okay, so what I mean by this is, can we find either a combinatorial interpretation of tau of n or some sort of other number theoretic interpretation of tau of n? And I'll mention one, sort of two different ways or two approaches that people have done in this strategy. So one is that it turns out that if you try to compute tau of p for a prime p, then you can think of this as sort of a weighted average of fp points. I should say number of fp points over all elliptic curves defined over fp. Okay. There's another instance of this strategy, which is, this goes back to, I think, Garvan and Schlosser. And they said this is, tau of n is actually sort of number of vector partitions for some, number of vector partitions for some league. But today's talk will be, I'm going to try to exploit this strategy by, today's talk, I'm going to show you guys that the Ramanujan tau function can be defined, or can be calculated to be the sum of a bunch of Gromov-Witten invariants of a smooth elliptic curve E. And the reason why this equality is kind of intriguing to me is because this right-hand side is completely determined combinatorially. You can write everything on the right-hand side purely in terms of, well, I'll explain it later, it's the irreducible characters of the symmetric group, and these things called shifted symmetric partial sums. Okay, so yeah, that is my trick.
Are there any post-trailer questions?
Where does 24 come from?
Yeah, 24 always shows up in this in this world. It's like so I think one interpretation is that it's the dimension of something. I can't remember exactly. It's like there are like 24 types of lattices or something like this. That's one reason. What I'll say is you can Google the 24 numerology about why it always shows up in the realm of elliptic curves, but I can't list all of them right now.
But delta is a really important modular form of weight 12 or 6, depending on how you count, and it's when you try to enumerate modular forms, it's you get some small ones like Eisenstein series and the discriminant, and after that, those kind of generate the ring of modular forms. These generate the ring of differential forms on modular curves.
Probably a naive question. With the primes in number 2 and 3, does that include 2, or is that odd primes?
Oh, for this conjecture? Oh no, for this thing.
For number 2 and the.
I don't know.
Okay, it's fine.
I'm trying to think.
It's fine.
It might, probably, yeah.
Probably.
Yeah, I think so. I think it includes 2.
Yeah.
I had to double check, but yeah, I'm pretty sure it does.
All right, if there's no more questions, a couple minutes to shake off, and anybody who needs to leave can do so, and then we'll start.